Welcome to the ninth set of notes for Lesson 2 of Introduction to Optical Design. We're going to continue on talking a little bit about the properties of glass. Before we said that optical design is simply sequentially applying Snell's law from surface to surface to surface as light propagates through your optical system, but what we're going to find out now is there's so much more involved than simply tracing the rays. We've got to fully understand what is happening to those rays as a function of the physical properties of the materials involved. So when we talk about the properties of glass, the important properties in terms of optical design are related to the index of refraction. Obviously, the index of refraction itself, which is simply a single number defining behavior at one single wavelength, and also the dispersion and partial dispersion. And these are related to how the index of refraction varies as a function of wavelength. But as an optical designer, there are a lot of other things you need to consider as well. First off, what is the cost of the optical material? There is a wide range of costs and availabilities of optical materials, and you need to make sure that you are making the most appropriate choices. What is the weight of the material? The density of the glasses varies significantly as well. What's the thermal expansion? How do its optical properties change as the temperature of the material changes, so the lens expands or contracts, changing shape, focal length if you will, which will affect your system performance. How hard is the material? How resistant is it to scratching? Resistance to staining, resistance to acid, how much light transmits through the material, and others as well. We're not going to concentrate too much on a lot of these physical properties, but we'll at least talk about them briefly. We're going to spend most of our time talking about the properties related to the index of refraction. Refractive index, or index of refraction, from now on I'm just going to say index, is the most important property of an optical material. And it basically describes how fast the light propagates through a material relative to how fast it would travel in effectively vacuum, but we'll see momentarily we really mean air. The index of refraction is dimensionless, and the definition is simply the speed of light divided by the speed of light in the material. Indices of refraction are effectively numbers typically larger than 1. In other words, the rays propagate more slowly in the material than they do in vacuum or the surround. The reason I'm saying the surround rather than vacuum is typically when manufacturers provide index of refraction data for their materials. You know, these are like the shot glass catalog, Hoya, O'Hara, Hikari. I don't mean to slight any fabricator, but those measurements are typically made in the room environment, near standard temperature and pressure, typically 20 to 25 degrees Kelvin, 1 atmosphere. So what we actually see in glass catalogs is a relative index, not an absolute index. And you'll need to keep that in mind, in particular if your system will be used in vacuum or in a situation where some of the materials are at one pressure and or temperature and other components are at a different set of environmental conditions. The important parameter to remember, though, is that when I list an index of refraction, I'm actually indicating a value at one particular wavelength. The index of refraction itself does vary with wavelength. It also varies with temperature, altitude, or pressure, humidity, and other properties, but the key is that it varies with wavelength. And this variation in index with wavelength is called dispersion, and we're all familiar with it. It's what happens when light hits a prism of some form or a crystalline material. In those instances, like the hanging crystalline chandeliers you may have seen in older homes or in movies in the past, it's very obvious that this dispersion is occurring, but it also occurs in our lens designs, harder to see with the eye, but absolutely present. So the dispersion results in a varying in focal length with wavelength, and we're going to need to correct for that. The variation in index of refraction with wavelength is a function of the optical material. No two materials behave exactly the same way. It is dependent upon the absorption spectra of the material. In typical optical materials, the index of refraction is typically higher in the blue than it is in the red, although there are special materials that do behave differently than this, anomalous type materials. We're going to concern ourselves with classical optical materials, at least in this course. Now, how do we understand what the index of refraction is at any wavelength we're interested in? There are devices called dispersion formulas. There are several different dispersion formulas that allow you to calculate the index at any given wavelength within some wavelength region. The optical design software has these built in, so within Zemax you can select any manufacturer's catalog, and for any wavelength in the valid passband it will be able to calculate for you exactly, or to some reasonable accuracy, the index of refraction. Okay. Index dispersion formulas are based on measured data. You'll need to have at least 2 wavelength index pairs, but really that's not enough. Typically dispersion formulas want 6 or more index wavelength pairs to get a reasonable fit. So if you have sufficient information, the dispersion formulas are going to be accurate over some limited wavelength band. Typically it's going to be limited to that range over which the data was measured. Do not extrapolate. If you have taken index of refraction measurements, or you have index of refraction measurements over the visible wavelength region, so from say 350 nanometers to 750 nanometers, do not try to use that information to calculate what the dispersion is at 1 micron. You could be very, very wrong. Okay? But what dispersion formulas do allow you to do is, at appropriate wavelengths, you can calculate the design parameters without having to specifically have the index of refraction measured at that wavelength. A significant cost savings. For the glass manufacturers, what they will do is measure the index of refraction at several wavelengths, and this is a list of commonly used wavelengths and the element that wavelength is referenced to, and also the spectroscopy designation that's also often associated with a particular wavelength. When we talk about the visible wavelength regions, for instance, we're talking about the wavelength region from the F through the D wavelength all the way out to the C wavelengths. So from 486 to 587 to 656 wavelengths, nanometer wavelengths is typically what we refer to as the visible wavelength spectrum when we do our optical design. Couple of dispersion formulas. The Sellmeier is probably the most commonly used these days. It is based on the absorption spectra of the material, which is where the coefficient terms come from. And in this summation, the N value is usually 3, but it also may be 4, 5, or 6 for some specific materials. Also a Cauchy formula, sometimes also referred to as a Schott formula, that was used quite frequently up until about the mid-1990s. Now most catalogs typically use the Sellmeier formula. It was an empirical relationship, so index of refraction was measured at several wavelengths, and basically a formula was determined to fit that data, and it looked something like this. Hertzberger, you might see reference to materials typically that were measured in infrared wavelength regions. It is also based on analytical calculations. And the Conradi formula, the one thing I want to mention the Conradi formula is that if you have a material defined by a Conradi formula, it typically means that a very small number of data points was available to do the dispersion fit, and it's a dispersion fit that allows a dispersion formula to be calculated with a very small amount of data. Please use data defined with Conradi formulas very, very carefully. Its accuracy is somewhat suspect. And a dispersion curve, these show dispersion for a couple of materials. Again, data from the ZMAX information we'll start to be looking at shortly. This shows the change in index with wavelength for the materials N-BK7, a crown material, and N-SF1, a flint material. And as you can see, the range of indexes vary and as a function of wavelength, and the variation in that index with wavelength is noticeably different between these two materials and between any two materials. So we will continue on in our next lecture also discussing some of the other properties associated with optical glass. Thank you.